De heer Jan-Pieter d'Anvers, master in de ingenieurswetenschappen in de elektrotechniek aan de KU Leuven, heeft aan de faculteit een proefschrift voorgelegd, handelend over Design and Security Analysis of Lattice-based post-quantum encryption. Ontwerp en veiligheidsanalyse van roostergebaseerde post-quantum encryptie. En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. Hij zal dit proefschrift nu verdedigen. Ik vraag aan de kandidaat eerst een uiteenzetting van ongeveer 45 minuten te geven over zijn werk. Daarna zal er gelegenheid zijn tot het maken van opmerkingen en het stellen van vragen. Meneer Jan-Pieter d'Anvers, u heeft het woord.
Dank u wel. Thank you for the introduction. I will remove this. Is that allowed? Okay. So, the internet is insecure. I mean, the internet is not even built to be secure. The internet is just a way for your computer or your laptop or your smartphone or maybe your bank card to communicate with other computers around the world. And so the internet works, but my pointer does not work. So does this work? Okay. What is wrong? Okay, so that will stay on there. So, the internet is still insecure. The internet is not even built to be secure. The internet is just a way to connect computers, to connect your smartphone or your bank card or your computer to other computers across the world. And how that works is that when your computer or your smartphone wants to send a message, then it will send this message to the next computer on the internet. And this computer will send it to another computer, and to another computer, and to another computer, until it arrives at the destination computer. But this also means that all these computers in between, they can just see your message. Even if you want to send confidential email, or even if you want to do an online transaction, an online payment. So everybody on the internet can just see what you send. And still you can do this online payment, and still you can do secure communication. So how does that work? And to explain that, we come to the first word of the title of my thesis, Design and Security Analysis of Lattice-based Post-Quantum Encryption. So encryption. What is encryption? Imagine that Alice wants to send a message to Bob. But in the middle, on the internet, there is Eve. And Eve can see everything they send. So clearly, Alice cannot just send the message to Bob. So what is Alice going to do? Imagine that Alice and Bob have a shared secret key K that Eve doesn't know. Now, what Alice is going to do is she's going to take this message, going to take the secret key K and encrypt the message into an encrypted message, what we call a ciphertext, CT. And Alice will transmit the ciphertext to Bob, and Bob will receive the ciphertext, take this secret key K, and decrypt it back into the message. Now, this works, and you actually know an example of this. For example, the Enigma cipher used by the Germans in the Second World War is an example of this. But nowadays, we use much more advanced codes to do this. For example, the Advanced Encryption Standard, which you use every day now. And this was actually developed here in Leuven, this code. This is the international standard. Now, there's one problem with this, and that is that you need this pre-shared key. And you don't necessarily have this pre-shared key with everybody you communicate with over the internet. So how do you solve this? Well, we solve this using a different type of cryptography, namely public key cryptography. So in this ID, what Bob is going to do is he's going to generate two keys, a secret key and a public key. And Bob is going to transmit this public key to Alice or to anybody. And Alice can now use this public key together with the message to, again, encrypt into the ciphertext. And then this ciphertext is transmitted to Bob, and Bob can take the ciphertext together with the secret key to recover the message. And Eve, who only sees this public key and the ciphertext, does not learn anything about this message or about the secret key. And also this works. In the 70s, this was developed, for example, RSA or elliptic curve cryptography, and this works. So why am I talking about this then? Well, there actually is a problem. And this is a problem. This is a quantum computer. Now, what is a quantum computer? A quantum computer is a new type of computer, that works with completely different mechanics, and it's based on the principles of quantum mechanics. And these computers are not necessarily supercomputers, but they're extremely good at solving some mathematical problems, maybe in medicine or in aerospace. But unfortunately, they're also extremely good at breaking the public key cryptography that we have now. So this means that once these quantum computers are completely developed, we have no security on the internet anymore. So that brings me to the second word in my thesis, which is post-quantum encryption. So we want to build encryption that is secure against these quantum computers. But we also want this encryption to run on our regular smartphone, on our regular laptop. So we want this to run on our everyday devices, but it needs to be secure in the future against quantum computers. So in this thesis, I will first give you an introduction of how we're going to build this post-quantum encryption. And then I will explain you our scheme that we built ourselves, Saber, and I will explain you about how we attack these schemes. So I will actually explain you in this lecture, in this presentation, how we make it in detail. So we will need some math, but don't be afraid, you will be able to understand it. So just follow me, it's not too difficult math. So what are we going to work with? We're going to work with numbers. Integers, so gehele getallen, numbers modulo q. This means that we're working with numbers between 0 and q, which is a certain parameter, a given parameter. So we can just multiply and add and subtract with these numbers. And if these numbers go over q, then we just subtract q until we're back between 0 and q. Okay? You actually know this. If you know how to work with time, that is. So if, for example, it is 10 o'clock now, then in 4 hours it is not 14 o'clock. Because if we're working with hours, we're actually working modulo 12. So if it's 10 o'clock now, then in 4 hours it's 2 o'clock and not 14 o'clock. Because we subtracted 2 to be between 0 and 12. Okay, so if you're a bit more into math, then just think that we're working actually with matrices. Matrices with coefficients modulo q. Matrices and vectors. And if you're really into math, then think we're working with matrices where the coefficients are actually polynomials. And so these are examples, so we will later use A, this will be a matrix, and then S, this will be a vector. So we're ready to explain post-quantum encryption. So the first thing I'm going to do is I'm going to just rearrange this picture a bit. This is exactly the same picture. And now we're going to fill in the gaps. So Bob is going to make 2 keys. So how does he do this? Bob is going to generate a uniformly random number A, completely random, and he's going to generate a small number S, or a vector with small coefficients S. And this S is going to be the secret key. The public key is going to be A and B, where B is A times S. And Bob is going to transmit this to Alice. Now Alice receives this public key, and she's going to generate her own secret small number or vector S prime. And she's going to multiply both A and B with S prime. And she's also going to add the message, because of course she wants to transmit the message. Now she sends this over as a ciphertext, and Bob receives this ciphertext. Bob takes his secret S, multiplies it with B prime, and subtracts these 2 terms. So what do we get? Well, if we follow the undermost bar, we get A times S prime. And if we follow the upmost line, we get A times S prime plus the message. So if we subtract these 2 from each other, we just get the message. Perfect, we have sent over the message. Now, is this secure? No, it's not. It's absolutely not secure, because remember, this public key is A and B, where B is A times S. So if you just do B divided by A, you recover the secret, there is no security. If you're working with matrices, this is just solving a linear system of equations. Now, we want security. So what are we going to do? We're going to base ourselves on a mathematical problem that is believed to be hard to solve. So what are we going to do? We're still going to have A, we're still going to have S, but additionally, we're going to sample another small secret E. E is a small noise that we're going to add to B. So B is now A times S plus E. And all of a sudden, if you choose the right parameters, it becomes hard to find S. It becomes even hard to distinguish this from random. So if you don't know S or E, this just looks completely random. There is no structure in this. And this is called the learning with errors problem. And that's what we're going to base our security on. Now, the learning with errors problem is actually a problem in a lattice. It's a mathematical problem in a mathematical lattice that you have to solve. And that's where this name, lattice-based post-quantum encryption, comes from. Because the problem that we're basing ourselves on to get security is based on problems in lattices. Okay, so we had our scheme, we have this S, S prime, we want to secure them, so we add this noise E, we add this noise E prime, and E prime prime, and now we have security. But now look at Bob. We have added all these errors to the message. So Bob does not receive the message, Bob receives the message plus this error. So, okay, we have security, but we cannot transmit the message anymore. So how do we solve this? Well, what we're going to do is, what you have to see is that this error term is actually smallish, because all these red terms are small. So if you multiply them together and add them together, they will still be smallish. And this is what we're going to use. So what we're going to transmit, remember that we're working between 0 and Q, like a clock. So if we want to transmit a 0, then we're going to transmit a 0. But if we want to transmit a 1, then we're going to transmit Q divided by 2. And now, if we send this over, this message, then what happens is that there's this noise that is added. But you can clearly see that as long as this noise is small enough, we can recover the original message. More specifically, if this noise is not bigger than a quarter of the circle, or Q divided by 4, we can just recover the message from this. So success, we have built a scheme where we have security because of this learning with errors problem, this error that we add. And we also have, we can transmit this message because of this trick where this noise is small enough and we work in this circle, we can recover the message. So this actually works. This is secure if Eve is just looking at this. So if Eve is looking, then A, B, B prime, and V prime don't give her any information about the message or about the secret. Now, there's one problem. This is the internet. This is the world, the Wild West. Eve can just send her own message to Bob. Eve can even send bad messages to Bob, badly formed messages, to try to see how Bob reacts to these messages and try to recover the secret of Bob. So Bob wants to check whether the messages that are sent to him are actually valid messages or bad messages. So how are we going to do that? Well, Alice is going to send over a key K, a key that can later be used, for example, for symmetric key encryption. And based on this key K, Alice is going to calculate S prime, E prime, and E prime prime. So all of these terms are going to be completely based on K. So if you know K, you can do the whole encryption. Now Bob is going to decrypt, he's going to find K, and he can actually also do the encryption. So he's going to do re-encryption, the same procedure as Alice. He will find the ciphertext, and now he can compare if the ciphertext that he found is actually the same ciphertext as he has inputted. And if that is true, he is happy, and he will just continue with the calculations. However, if this input ciphertext is not the one that he calculated himself, he knows that something fishy is going on, and he will just stop communicating or calculate on randomness, doesn't matter, but he will not reveal anything about the secret. So this is actually all there is to know about post-quantum encryption. Well, it's not all there is to know about post-quantum encryption, but now you know how post-quantum encryption actually works. So just to give you an intuition, what are the sizes that we typically work with? So if you're thinking in terms of numbers, think numbers with 2,300 digits, so quite big numbers. If you're thinking in terms of matrices, think matrices of size 268 by 768 by 768. And think that these coefficients are between 0 and 8,192, so 2 to the 13. And if you're thinking in terms of matrices with polynomials, think that your matrices are 3 by 3, for example, but your polynomials have 256 coefficients. Okay, just roughly, this is the sizes that we work with. So this is essentially what I had to learn at the start of my PhD. Now, another important thing that happened at the start of my PhD is that the American National Institute for Standards and Technology, these are the people that decide on the de facto standards on the internet, they decided to hold a competition or a process to find a new encryption standard that would be secure against these quantum computers. And so we decided to design our own scheme and to submit it to this competition, and this would later be called SABRE. So SABRE is work together with Anshuman Karmakar, Sujoy Sinharoy, and Frederik Verkouteren, and later also Andrea, José, and Michiel joined the team. So what is the idea behind SABRE? The idea is that we have this key. Before we had this key, and to have security, we added some error to this key. Now the idea in SABRE is we still want an error, but we're going to have a different error. We're going to compress. And this compression will, one, give us a certain error for security, but also it's going to give us smaller things that we have to transmit because we've just compressed them. So that is the idea, the big idea behind SABRE. Of course, we want security, and we based ourselves before on this learning with errors problem because this was mathematically secure. But luckily for us, there was another problem out there, which is called the learning with rounding problem. Now, how that works is that we still have this A, we still have this S, but what we're going to do now is we're going to scale from modulo Q to modulo P. So we're going to divide by a certain factor, and then we're going to round. And now, all of a sudden, it's also hard to find this, and it's also hard to distinguish this from random. Let's give an example, then it will become clear. Imagine that A times S is 93,572. Q is 100,000, and P is 1,000. So what are we going to do? First, we're going to scale. We're going to scale this by a factor 100, so we get 935,72. And then we're going to round to 936. And you clearly see that, one, we have introduced an error, and two, we have to send over less digits. So how do we incorporate this in the scheme from before? Well, instead of adding these errors, we're going to scale. We're going to scale and round, and this will give us security. Now, the next two slides are a bit more technical. Later, we will go back to a more intuitive explanation. So how did we design SABRE? The first thing is what I already explained. We base ourselves on learning with rounding, which has the advantage that the public key in the ciphertext will be smaller. And also, we don't have to generate these E-terms, which in some circumstances actually is expensive. The second thing is that we have this, that we chose power of two moduli. This means that our arithmetic operations become easier. So it's easier to round, it's easier to do modular reduction. And the reason is you can also see in humans. If you have to, for example, multiply by 10 or divide by 100, powers of 10, this is easy for humans to do. Now, computers only work with two numbers, 0 and 1. And so for them, it's easy to do this calculations modulo 2. Also, an added advantage of this is that you can actually compress the public key, which is not as trivial to do if you have non-power of 2 moduli. The drawback of this choice, however, is that the multiplication becomes a bit more involved. So most schemes actually choose a certain prime with a certain structure because they can use entity multiplication. And entity multiplication, number theoretic transform multiplication, is a bit like the fast Fourier transformation. It's an efficient way to do this multiplication A times S. And so in SABRE, we cannot do this out of the box. We have to use or different techniques or do some pre-processing before we can use this entity. Okay, and the third thing is that we use module LWR. So in essence, what we work with is not just numbers or matrices, but we work with these matrices of polynomials. And now the polynomials will always be in the same ring. We'll always have the same size, so we will always have 256 coefficients, which is efficient and simple, because if you implement it, you only have to implement it for this one type of polynomials. You only have to implement all these computations for this one type, and you can really put all your focus on optimizing this operation. on the other hand, we want to scale for security. We want different sizes for security, and that we can do with this matrix. So if this matrix, for example, is a 2x2 matrix, we will have the low security version of Sabre, while if we take it as a 4x4 matrix, we will have the high security of Sabre. So this gives us flexibility. Okay, so here is a scary table with a lot of numbers. If you do all the calculations and the parameter settings, you get all of these numbers which define Sabre. I will not go through all these numbers, so rest assured. I will just point out a few things. So first thing is that Sabre comes in 3 versions. There is Sabre, the regular security version. There's Fire Sabre, the high security version, and then there is a light security version of Sabre. I'm afraid to say the name because, yeah. And then the second thing is that I want to point out is that Sabre has a certain failure probability. And this will come back later in the presentation. But so there's a certain probability that Alice sends a message to Bob, and Bob will not be able to decrypt this message correctly. But this probability is extremely low. So this probability in Sabre is 2 to the minus 136. That is an extremely low number. Still, we will come back to this later. The second thing is security, because that's what we want, right? How secure is Sabre? So we say that Sabre has a security of 172 bits. And this essentially means that if you want to break Sabre, you have to do at least 2 to the 172 operations. Just to give you an idea, the number of atoms on the world, on the whole Earth, is actually smaller than this. So you need to do more operations than the number of atoms on the whole world. This is quite secure. How did we determine this number? This is actually how hard it is for Eve to recover the secret key S from Bob, or how hard it is for Eve to recover this S prime from Alice. So in essence, it is how hard it is to break this learning with rounding problem with the same parameters. And we can even prove this. We can prove that the security of Sabre, or the probability that an adversary can break Sabre, in essence, is the probability that he can break Bob's problem, or that he can break Alice's problem. But then if we try to prove this, there is these 2 other terms that pop up. And so especially this last term I want to focus on, because this involves this delta, this failure probability. And this term essentially says that if your failure probability is too high, then we cannot prove security. It does not mean that Sabre is insecure. It just says there's a gray zone. We don't know really what happens. And so when we designed Sabre, it was not really clear what really happened in this gray zone. So we picked a certain failure probability, but we were in this gray zone, so what does this mean? And this is what I will talk about in the next part of the presentation. But before that, I can proudly say that Sabre, at the moment, is one of the finalists in this process to develop the new worldwide standard. So Sabre is one of the 4 finalists in this process, and I'm quite proud to announce that. But how this ends, we will see. We're still in the 3rd and final round. Okay. So, 3rd section, we will look at this decryption failure probability. And so this part is based on a few papers, together with Frederik Verkouten and Ingrid Verbouwede. Another paper together with Melissa Rossi and Fernando Verdia. And then a 3rd paper together with my thesis student, Senne Batsleer. So what is the idea? The idea is that we're going to be Eve. We're going to be Eve, and we're going to try to break the security of Sabre or of other schemes. So we're not only targeting Sabre, we're targeting all lattice-based encryption schemes. So we're going to be Eve, we're going to try to break these schemes just to see if they're secure, because if we can break them, they're clearly not secure. But if we can't, we have more confidence in that they are actually secure. So what are we going to do? We're Eve, and we're going to submit ciphertext to Bob. And Bob is going to decrypt this ciphertext, and we are going to see if Bob actually is able to decrypt this correctly. So we are going to look for these decryption failures. Now, if we find these decryption failures, then we can actually reduce the security of Bob. We showed that in our work. You see here on the x-axis the number of failures that you already have found, and on the y-axis you see the remaining security of Bob. You see that security goes down if you find decryption failures. I will not talk about this. What I want to talk about is how we can find these decryption failures efficiently. Because remember, these only happen with an extremely low probability. So can we speed this up? So first, remember what these decryption failures were. These decryption failures happen if this error is too big. So if this error term is bigger than q divided by 4. So this is what we're working with. Now, just for the sake of the presentation, let's simplify this. Let's group all of these Bob's terms, all of the secrets that we want to know, in a secret vector. And a vector is essentially just an arrow with a certain length and a certain direction. Okay? And we're also going to group the ciphertext terms, the terms that we decide in the ciphertext, into C. And this is also a vector with a certain length and a certain direction. And then we're going to say for the presentation that E prime prime is 0. It's small compared to the other terms, so let's just say that it's 0, that it doesn't exist. Now, given this approximation, we can simplify this failure condition. This failure condition becomes now that the inner product between these vectors, we have a failure if this inner product is bigger than q divided by 4. Or, graphically, this means that there is a secret vector in a certain direction, and based on this direction, there is a whole area in space, and if our ciphertext falls in this area, we will have a decryption failure. Okay? Now, more in detail, actually, decryption failures will happen based on 3 conditions. The first one is if the secret length of this vector is larger, then we will have a higher probability of a failure. If the ciphertext is larger, then we will also have a higher probability of failure. So this is what you see. And also you can see this graphically. So if the length of this ciphertext is going to be bigger, then there is a higher probability of failure. And then there is this third term, this cosine term. And this term says that if our secret and our ciphertext are in the same direction, then we will also have a higher probability of failure. And also this you can see from this figure, because imagine that your ciphertext is perpendicular, so lotrecht on the secret, then you will never have a failure, because they're not in the same direction. So they need to be more or less in the same direction. Okay, so remember the goal. The goal is to find a ciphertext that fails with a high probability. So let's look at the 3 conditions. The length of S, well, we don't know the length of S. We cannot influence the length of S, so we cannot do anything with this. So the direction of the secret in the ciphertext. If the ciphertext is in the same direction, then there's a higher probability of a failure, but this is unknown because we don't know the direction of a secret, so we don't know in what direction this, we have to look. So we cannot do anything there. And then there is the length of the ciphertext, the third property. And this we actually know. We want to have long ciphertext vectors. So if we find ciphertexts with ciphertexts that are long, then we actually have a higher probability of a failure. So we just choose extremely large ciphertexts and problem is solved? No, because remember that Bob is checking us. Remember, Bob is doing this process. So if we submit invalid ciphertext, then Bob is just going to reject us. So we need to submit valid ciphertext. So back to the drawing board, how are we going to do that? We're just going to generate a huge number of valid ciphertexts. And we're only going to keep ciphertexts that have a certain length. So ciphertexts that are outside a certain circle. Okay? And now if we overlay this circle with this area, you can also clearly graphically see that these ciphertexts will have a higher failure probability. So instead of just random guessing, what we do is a 2-step process. We do a pre-computation to find weak ciphertexts with a high failure probability. And in the second part, we hope that these will trigger a decryption failure. And these will with a higher probability. And actually, the first part of this process, we can speed up using a quantum computer. So using a quantum computer, we can speed this whole process up using Grover's algorithm, which is an algorithm that allows you to do searches more efficiently. So if you combine all of this, you can put it in a graph and see what the cost of the attack is. So what you see on the x-axis is the work that you do in this pre-generation phase. So in essence, it's the length, the diameter of this circle. The longer you make this diameter, the further you go on the x-axis. And on the y-axis, you have the cost of the attack. And you can see that if we don't do any generation, we have a certain attack cost. And if you start to do this pre-computation, which we call failure boosting, you go down in attack cost. But only so much, because after a while, this pre-computation becomes so expensive that you gain nothing. So there is this sweet point. So we have reduced the cost of finding one decryption failure a bit. Now, can we do better? Yes, we can. So once we have found a decryption failure, we can actually start to bootstrap this whole process. Because remember, if we find the decryption failure, we know something about the direction of the secret. Because this ciphertext is going to be kind of in the direction of the secret. And this information we can use, because we're still looking for a new ciphertext that fails. We still don't know anything about the length of the ciphertext. We still know that we want large norms ciphertext, but now we know kind of the direction of the ciphertext, of a secret. So instead of looking in a circle, we can actually start to look in an ellipse. And if we now plot this ellipse over our area, you can see that there is a better match between this ellipse and this area than between this circle and this area. And so this better match will lead to a speed up. And this you can see in this graph. So on the x-axis, you have the number of failures that you have already found. And on the y-axis, you see the cost to find the next failure. And so you see that it clearly goes down. Now, it might not seem that it's going down that much, but it's actually going down a lot, because this is a logarithmic graph. So if you go from having one ciphertext, failing ciphertext, to having two, then it goes down with a factor 8. And if you go from having 2 to having 4 failing ciphertexts, you go down with a factor 4,000. So in essence, this means that your cost is completely dominated by finding this first failure. Okay, so you have to do a lot of work to find this first failure. Once you found it, all the rest of the failures are easier. So in essence, the attack is dominated by finding the first failure. So we've calculated this whole attack, and we've actually applied it to a scheme that was submitted to this NIST post-quantum standardization process, SS-entropy-KA, which claimed an even higher security than Sabre, claimed a security of 198 bits. And we've shown that using our attack, even taking into account practical constraints about our attack only costs 96.6 bits. So this scheme is essentially broken, or at least the security is halved, which is quite serious. Now, as for the impact for Sabre, or for example, other candidates in this competition, there is no impact. The attack works, but the attack is more expensive than breaking this learning with rounding or learning with errors problem. Okay, so you'd rather do that than do our attack. Okay, so we've just seen attack, but we're gonna do better, because we're gonna cheat this time. We're gonna try to break the schemes really, really, really fast. So this part is actually based on the second work here, together with Marcel Tiepelt, Frederik Verkouter, and Ingrid Verbouwheden. And the idea is based on this. So there's 2 sentences that I would like you to read. Okay, so one of the sentences was probably easy to read. It was a sentence without any errors. The second one was probably a bit harder to read, because I have introduced errors in the sentence. So if there's errors in the sentence, it becomes harder to discover the true meaning of a sentence. And this is actually also true for computers. Sometimes if you write code and if you're not careful, then your code will take a longer time to execute than in other circumstances. And this is what we're going to use. So we're still Eve, we're still trying to break the scheme. So we're still submitting ciphertext to Bob. And Bob is going to decrypt, but now we're going to cheat and we're going to send in bad ciphertext. So what will happen? We send in a bad ciphertext, Bob is going to decrypt. Wait, I did not explain one important detail. We're going to target a specific type of lattice-based schemes. So the designers of these schemes, they had a really cool idea, which is that we have this error probability, and this error probability needs to be extremely low. So what do? Well, we're just going to do error correction. We do error correction so that this error probability becomes much lower. So how do we do this? We're going to send this K, or the message K, or a secret key K. We're going to send this over, and we're going to encode it. For example, we're going to send it over 3 times. Now we send over the message, Bob is going to decrypt, and now Bob has 3 times the message, which might be noisy. But because he has his message 3 times, he can correct errors in this message. Now, in reality, this is not the best way to do it. So these schemes use a better technique to do error correction with error correcting codes. But essentially, the idea is the same. So now we can start the attack. So Eve is going to submit ciphertext, bad ciphertext, and Bob is going to decrypt them. Bob is going to correct the errors. Bob is going to find K. He's going to re-encrypt, and he will see that we're messing with him, that we're sending in bad ciphertext. So he will not give us any information. But remember from before, we have this error correction, and if Bob is not careful, then it might take longer time to do this error correction if there is actually errors in Bob's ID key. And if there's no errors, Bob might execute this very fast. So this is what we're going to use. So we're going to send in a ciphertext. What ciphertext are we going to send in? For example, this ciphertext. We choose S prime to be 0. We choose E prime to be 1, or if you're thinking in terms of matrices and vectors, a 1 with all zeros. And we choose E prime prime to be Q divided by 4, or Q divided by 4 and all zeros. Then if we rewrite this failure equation, well, we first get a 0, then we get 1 times S, and then we get Q divided by 4. So we get this, and more simplified, we get a failure or an error if S0 is bigger than 0. So we input this into Bob. Bob is going to decrypt. And then based on what S0 is, Bob will take a long time or a short time. And based on this, we learn what this value is of S0. And we can construct different ciphertexts to learn different information about this secret key. And this attack we can actually really do in practice. So what will happen in this attack is that we do the decoding 2 times. So first we send in a ciphertext to Bob that's going to take him a long time to decrypt. And then we're going to, so one with, for example, an error. And then we're going to send in a ciphertext that takes a short time with no errors. We're going to measure these 2 times, and then we're going to input our own ciphertext and just one by one do these measurements and recover the key. And I can, this is dangerous, of course, but I can try to do this in real life. So what you see here is every time that there's a new line, we do a timing and we recover some information about this scheme. And if we let this run for, let's say, 5 minutes, then we can recover the whole secret of this scheme. This is, for example, an attack on Ramstick on the code that they wrote themselves. Okay, so this clearly shows that designers need to be careful when running this code. Let's go back to the presentation. What have we learned? So we've learned how to do lattice-based post-quantum encryption, and this is really how it's done. So you now know, well, don't do it yourself, but you now know how to secure the internet in the future, essentially. We've also seen the specific properties that Sabre has, where we tried to design our own schemes, apparently successfully. Then we've shown how we determine the security by trying to attack these schemes using decryption failure attacks. And we've shown that if you're not careful with implementing it, even though your scheme might be secure, if you make this implementation faults, or if you're not careful in implementing it, then you can break the scheme using not the mathematics, but really just trying to break the scheme while it's working on a regular computer. So I've just selected for the presentation 3 works. I have worked on different things also during my PhD. For example, protection against these side channel attacks, so timing attacks or attacks that make use of power consumption. I've also looked at different decryption failure attacks. And I also developed a new technique to avoid this, this re-encryption step, because Bob has to do essentially a decryption and an encryption, which is quite expensive. So we tried to find a new way of checking the validity of inputted ciphertexts. So I will end with some ideas for future work. And the first one is decryption failures. What can we do with decryption failures in future work? So the first thing is that we only aimed our attacks at some schemes. It would be interesting to look in the future at, for example, schemes that use error correcting codes, because there's really problems if you go from the schemes that we look now to schemes with error correcting codes. We don't know if the attacks will really work. Or also maybe even look at these decryption failures as attacks for code-based crypto or other cryptographic primitives that have these decryption failures. The general framework actually should work for other schemes also. So this failure boosting idea at least. And also we can look at the security proof, because I said before that we had this security bound. There is this certain that we can prove, and then there's the attacks. And there is still a gray zone in between the two. So we can try to improve the security proofs so that this gray zone becomes smaller and that we have more idea of what the right choice is for decryption failures. So the second thing is side channel protection. I showed you one side channel attack based on timing in this presentation, but there's different side channel attacks that you can do. For example, measure the power of your computer or measure radiation that comes off your computer. And if you really want to implement crypto in practice, you have to protect against this. So ideas here, or at least work that is really important to do, is look at higher order masking of schemes. Look at specific building blocks. So there are specific building blocks that if we try to protect them, they become like 50 times more expensive, or maybe 200 times more expensive. So here, if we can improve this, we can really improve the overall performance for protected implementations. And we can look at protection, other protection mechanisms, such as shuffling or protection against fault attacks. So a third area that would be interesting is this error correcting codes. So we've attacked schemes that uses error correcting codes, but it is still a pretty cool trick. At least I like it. It's a really cool trick. So in the future, I believe that actually this is really a way to improve lattice-based post-quantum encryption. So what could we do? So first, on a more mathematical or theoretical thing is look at more appropriate error correcting codes that are maybe more performant. For example, codes that use soft error correction. I mean, there are already schemes out there that do something like that, but then the codes are not super advanced. So I think we can really play with better codes here and get better results. Other ideas might be like a confirmation hash, like used in Ramstake, might also be cool to implement. And then, of course, if we want to implement this, we need to have this side channel protected, which is not going to be easy. So this is also a topic that might be interesting in the future. And then the last thing is error term checking. So this is new transformation that we made, and we showed that for a specific scheme, tree bears, we could increase the decryption cost by 36%, so much faster. The problem is that it's a bit constrained, so we cannot apply it in every context, we cannot apply it for every scheme. And the question is, can we actually extend the range of what we can do? Or maybe can we design schemes that are specifically designed to match these criteria, and is this actually better? Also, I think we can really improve this implementation. So our implementation was a bit basic, was just to show the principle, but we can really use some properties of this to speed up the whole decryption or decapsulation. So with that being said, here is my bibliography. And that was the end of my presentation, so I would be happy to answer any questions. Hier. Is er nog niet aan?
Dank u Jan-Pieter voor deze boeiende uiteenzetting.
Dank u wel.
Het is tijd om wat vragen te beantwoorden.
Yes.
Ik zal eerst de leden van de examencommissie voorstellen. De eerste die zijn vragen zal voorleggen, the first one to ask you questions, is Damien Stellé van de École Normale Supérieure de Lyon in Frankrijk. Second will be Sujoy Chinya Roy van de Security and Privacy Group van de University of Birmingham. Both of them follow your public defense online.
Yes.
Next we will have, to my far left, in the first row, Frank Pieces. He is also secretary of this commission and is linked to the Department of Computerwetenschappen. Vervolgens hebben we Nigel Smart van het departement elektrotechniek. En dan komen er 2 personen nog van het departement elektrotechniek. De eerste is Frederik Verkouteren, hij is co-promotor van dit werk. En dan Ingrid Verbouwen, die penvoerend promotor is van de thesis. Ikzelf ben Patrick Wollens van het departement materiaalkunde. So, Damien Stelle, please, you can ask your questions.
I will try to get you on the screen.
Can you hear me?
Yeah, we can hear you.
Okay, excellent. Okay, so first I want to congratulate you on your PhD manuscript, which was very pleasant to read, and also thanks a lot for this very nice presentation.
Thank you.
Okay, so I have general questions. So a large part of your work and also of this presentation is about the impact of the noise on decryption failures and on security. So the attacks that you give can be viewed as security upper bounds. There are also security lower bounds coming from security proofs namely of the Fujisaki-Okamoto transform in the quantum random oracle access model. And they don't match this upper bound and lower bounds. So what is your opinion? Can we improve the attacks? Can we improve the lower bounds? Where does the truth lie?
So, in my opinion, I think that most gains can be made in the security proofs. The security proof essentially say, or at least go out from a model where you can completely predict if a ciphertext is going to fail. Like, they assume that you have complete knowledge of the secret to do Grover. And this is clearly not, from an attacker's perspective, it is clearly not possible. So I think there is the most work to be done at the provable side. So trying to improve these proofs to match this bound better. And I think an interesting work in this direction is actually, so there is our approach, which is failure boosting and directional failure boosting. But then there is a very interesting paper by John Shank and Nina Bendel, I think, looking at what happens if you find the successful failure. Because I think you can limit the proof by finding the first failure. So in the proof, you don't have to really care about finding all of the failures. If you can say that if you find a decryption failure, essentially the game is over. So I think that is what a proof should end, or at least that is close enough to the truth for if you try to improve the proofs. But this paper looks at what you can do if you find successful failures, because successful decryption. So successful decryptions will also give you some information, and so taking this into account in the proof will be, I think, the main challenge if you want to improve the proofs. If that makes sense to you.
Okay, so if I go in the same direction, okay, so your guess is that the proofs can be improved, or that they don't reflect reality of the attacks, of the potential attacks. Okay, so let's if we could improve proofs, the lower bounds. Do you think it's feasible with the same set of hardness assumptions that we currently use, or that would require some kind of ad hoc, reasonable assumptions to be closer to reality?
Okay, this is a really hard question. So I would have liked to find a more elegant way to describe this failure boosting process, kind of like an entropy-ish way to describe it. But I've thought about it a long time and I haven't found anything. But maybe it's nice if somebody else looks at this. This might be a nice way to describe this, but I don't really know a way to describe in a way what is failure boosting is doing. So I'm not not looking at really at the attack side, but just looking at finding this first failure in this failure boosting thing. If we find a nicer way to describe this, this might help, but yeah, I haven't found it. This is a bit frustrating, I think, because I don't know if it exists even, but I think something like that might be a step in the right direction in understanding this. But yeah, I don't have really any leads on that directly.
Yes, thanks. So I have another one related to noise. Okay, so first from the cryptanalysis side, or also from the lower bound side, does the choice of the noise distribution matter? For all of this, all that we know is orthogonal to the specific choice of noise that is considered.
Then specifically for decryption failure attacks, I assume. So yes, but it depends on how your scheme is built. I will give an example. If you're, for example, looking at this lattice-based encryption schemes that use error correction, we've shown in this paper on in the dependencies between the errors, that there, if you use heavy error correction, it might actually be good to use constant norm secrets and constant norm ciphertexts. So in this failure boosting, maybe for the public, in this failure boosting, you have this long ciphertext and short. So what if we limit all the ciphertext to the same norm? This might help, especially if you use error correcting codes. For other schemes, the difference is smaller. So there you can do it, and it gives you a certain speed up, but it also comes at the cost of course, you have to implement this, and it might be more difficult to implement than just independent coefficients. So there is a trade-off, and it's not clear that it's better to use constant norms, ciphertext or constant norm secrets. So, like roughly, I would say that if you're using, if you don't use error correction, then probably, I mean, it's a trade-off, but probably you're better off with just the way it's done now. If you're going for heavy error correction, I would say that it's better to go for constant norm secrets and constant norm ciphertext. Then if you, for example, for Sabre, which has no Gaussian distribution, I think it matters less, because if you add up all these error terms, it becomes Gaussian-ish. But there might be a way to improve it a little bit, because you have slight information about the direction of a secret. Because if all your coefficients are like Gaussian distributed, then there's really no direction. But if they're all uniform distributed, then there is kind of a sense of direction. Now, because this is high dimensional, I don't know if this is really usable in an attack. But yeah, there is, again, a trade-off or something to take into account. But I think this is less important.
Yes, thanks. So I have a more general question, and that will be my last. Okay, so you designed Sabre at the very start of your PhD thesis, and I think it's a great scheme.
Thank you.
And you spend, if I simplify, you spent your thesis analyzing the schemes that you introduced at the start. Mm-hmm. So now that you are at the end of your PhD thesis, would you design the scheme in the same way? Would you change Sabre, or would you do it differently, or you're just happy with your first guess?
No, there is some things I would change, but not too much. The reason I think not too much is how we design Sabre, which is really look for a simple and elegant scheme. So we didn't choose to have error correction. We didn't choose to have really advanced things. And the reason is that, I mean, we wanted to have like a submission for an international standardization. So we really did like a safe bet on that. And I would, at the moment, still go for a safe bet. I mean, I think in the future, in 10 years, we can go for like more advanced schemes. We're not ready yet. We're really not ready yet as a community. So a safe bet is good. Now, what I would change in Sabre is maybe did propose in the last NIST submission a version of Saber, use Saber, which does not have binomial coefficients, but has uniformly random generated secrets. Also, not only the errors are uniformly random, but also the secrets are uniformly random. And this gives you some very nice advantages, for example, if you want to do side channel protection. Because this binomial sampling, you have to add up Boolean samples and it become arithmetic. It's a bit annoying, but if you use just uniformly random, you need less randomness, so less hash calls, which is really cool because protecting that is expensive. You need, you don't need to do this whole procedure. So it's simpler, it's easier to side channel protect, and it's also more beautiful, more elegant, which is also nice to have. I mean, elegancy is weirdly underestimated. It's really important to have elegant schemes because for some reason it gives you more security. I mean, it's hard to explain. So essentially, this is, I think, what I would change in Saber is this errors I would choose as uniformly random. Yeah.
Yep, thanks a lot.
Thank you.
So Joy, may I invite you to ask your questions?
Thank you very much. Thank you, Jan-Pieter, for the great presentation. It was really great. I do not have too many questions. Most of my questions are in the private data. Here I have more general type of questions. So you actually explained Saber using a high-level diagram, and there you showed different blocks. Okay, so I have one about internal blocks of Saber. So, for example, like let's say two parties are using Saber for if they use two different random number generators. Would that be a problem?
Could you repeat the last sentence because you're coming through a bit?
Okay, so let's say there are two communicating parties, and if one party uses a different type of random number generator, for example, say Trivium or some other thing, will that be a problem for Saber?
So the question is whether you can replace the hashes, for example, with other hash functions.
Yeah.
So everybody needs to agree on the same hash functions. The reason is that we have this re-encryption. So if you're re-encrypting, you actually need to come to the same result. So if you use a different source of randomness, or if you have a different way to get to the ciphertext, then this will not work. So you can in Saber substitute it, but then both Alice and Bob needs to substitute this change. Yeah.
Okay. Saber also requires two random number generators. And what will happen if there is some kind of bias in the underlying two random number generator?
Sorry, could you repeat the question?
Okay, I don't know what is happening. So can you hear?
Mr. Sujoy, we really can hardly understand you. Can you make the sound a little bit better?
Or maybe type the questions that
Or type your question in the chat.
Okay. Maybe I type it here.
So what happens if the random number generator is biased?
Yeah.
Yeah. So the question that we understood is whether what happens if the random number generator is biased. That is actually interesting. So we can go from like a worst case scenario. If your random number generator is completely biased towards one thing, then clearly you have no security. So, I mean, because, for example, if your matrix A is generated as all zeros, then, I mean, you're just generating on all zeros, and then you will just see the messaging clear. So that is not a good option. So, yeah, there clearly is, if your random number generator is too biased, then clearly you have a security hazard. Whether you can have small biases, for example, this is an interesting case study. So in round two, this is a submission to this process. So this random matrix A is generated uniformly random, and they used like a hash function, but not a complete hash function to generate this A. So there might have been some structure in this A, and they claimed that this was not important because you only need statistical, not like security randomness, but statistical randomness. Now, this is understudied, and I don't think we know really what happens if you do that, but it is an interesting avenue where you could speed up this generation of A. I wouldn't recommend it for the generation of S, just out of caution. Maybe, I mean, it's not really devastating, but I wouldn't do it. This is your secret, so yeah, just use good pseudo-random generators. If that is an answer to your question.
Yeah. Thank you. My next question is about multi-target attacks.
Yes.
So you mentioned that in the multi-target setting, the attacker has an advantage. Now my question is like, are there practical multi-target attacks?
So I think, so this failure boosting you can also do in a multi-target attack. And the reason that you want to do this multi-target attack is because you have to send queries to somebody. You have to ask for decryption. And if you ask for like a huge number of decryptions, this is hard. But we said before that essentially the first failure is the most hard. So what if, for example, there's a whole network of IoT nodes, and one IoT node can only do so many decryptions. I mean, this is a small computer, it's not super fast. So the nodes itself can only do a limited number of operations or decryptions. But if you have this whole network and you can probe all of these nodes, then you can actually, in the same cost or in the same thing, you can probe multiple nodes and thus increase your target. So I think there is actually a practical application of these multi-target attacks in this Internet of Things scenarios where you just want to target one node of a whole network and you can divide the load of finding these ciphertexts over this whole network. So I think this is actually a practical attack that you have to take into account. Whether these parameters of 2 to the 64 targets and 2 to the 64 number of queries are actually reasonable, this is another thing. I think these are a bit over-conservative, but maybe that's also fine in the current state of our cryptographic schemes. But the attacks themselves are I think, really, yeah, we should really take these into account.
Okay, thank you. My next question is a bit of different kind of question. So you developed cryptographic as well as cryptanalytic algorithms, and they perform quite a lot of computation. Now, assume that processor manufacturers, for example, say Intel or AMD, they want to design new generation processors, and they want to consider post-quantum cryptography. So they want to develop processors that will work in the post-quantum world and will run such algorithms efficiently. And they come to you, and do you have any suggestions for them such that they can design their hardware to support these algorithms in a better way?
You're trying to steal my grant applications, Sidray?
Oh, okay. I don't know.
No. I'm just joking. So I think, especially in high-end processors where maybe side channel protection is, I mean, there is a lot of background noise, so maybe side channel protection is less important there. The big focus will be on these multiplications, just getting these multiplications on as quickly as possible. In smaller processors, if you really need to implement side channel protection, then you see that the costs, because these multiplications and the hashes, so these are the two things, they're the most expensive parts. So if you can speed up these two, essentially you speed up the whole scheme. I don't know the numbers, but they might take up 50 to 70% of the time. If you go to more embedded devices, then these protection mechanisms, they scale worse at some of the building blocks, and there you could improve that. But I think we first need to improve them, just the theoretical models there, and then we can move on to practical, practical implementation aspects. So I would recommend to start with efficient polynomial multiplications.
Okay, I see. Yeah, but so such a multiplier will be quite big in area. So yeah, that could be an expensive design choice. Okay, Yeah, my next question is about your future work. So you mentioned that you would like to investigate error correcting codes to improve performance of lattice-based schemes because they can help reduce your parameter size. Now, like, what is your opinion about this? Like, how much reduction in the parameter size will be satisfactory, or is there any kind of lower bound on that? Or like this parameter reduction will go on indefinitely and you get better performance.
So is the question, if I can repeat, because you're coming through a bit rough, is the question is whether how much I think error correcting codes can help in lattice-based schemes.
Yeah, that's one thing. And like my second question is, because they help reduce the parameter size, so, is there a kind of lower bound on the reduction in parameter size, or like you can keep such a reduction going on?
So if there's a lower bound. Okay,
Yeah.
so yeah, error correcting codes can reduce the parameter size. We have seen this with LAC. So LAC is a submission to this competition also that uses these error correcting codes and has way smaller parameters. So that is cool. The second cool thing I think is that we can shift the load. So what you can do is mostly this encoding into these error correcting codes. It's not that expensive. It's not that hard to protect. So essentially, the one that is encrypting has an easier job, has to send over less bits. So this is nice. And then all the load of the computation comes to this decryption. And if you're in a scenario where this decryption is happening in like a central node, this might really be cool because here you're less constrained than in the encryption scenario. Now, for the lower bounds, so LAC, for example, has, so the size of LAC is 2 to the 8, so all the coefficients are 2 to the 8, and they have like 1024 coefficient polynomials. I think that's near the lower bound. I don't think, maybe we can shave off a few bits, but this is gonna be, I mean, like 2 to the 6 moduli, I don't think that is possible. Maybe it is, but I wouldn't bet on it, at least. So I think LAC and maybe a bit below LAC, but LAC is gonna be a lower bound. What we can improve in LAC is the choice of the error correction. Maybe we can find an error correcting code that is easier to protect, that is easier to do in these schemes, but that still has more or less the same capabilities or properties. So yeah, but I think LAC is kind of like the lower bound-ish.
Okay. Thank you. Those are all my questions. I do not have any more.
Thank you for the questions.
Thank you.
Frank, wil jij de microfoon hebben? Dan laat ik hem even bezorgen.
Dat is misschien wel handig, dan kan het publiek meevolgen.
Also from my side, Jan-Pieter, congratulations on the thesis, but also on the excellent presentation today. I read in your CV that you did several science communication projects, and it shows.
Thank you.
It was a very well done presentation. Thank you. So let me start with a very general question. So it's clear from your work and even from your presentation today that crypto is facing a wide variety of threats. You have very esoteric things like there's a new post-quantum machine coming up leading to an important threat to existing algorithms, and you have more less esoteric problems, like you can have an algorithmic error or you can have an implementation error, you might have a side channel vulnerability. There's all kinds of threats that the algorithms that you crypto guys design face. Yeah. What I want to ask you is, for this entire threat landscape, what is your view on this? What are the most important ones? Are there ones that receive too much attention? There's now a lot of attention on quantum machines. Are there others that receive not enough attention? So can you give me your view on what the most dangerous things are that crypto is facing today?
Okay, where to start? So yeah, we need to do all this crypto, but in essence, there's a whole stack, and probably most of the attacks are going to be social engineering. But this is not my job, so I will not talk about the social engineering part. But this is, I think, really just teaching people how to be safe on the internet, which is extremely hard. I think is the biggest challenge and also the hardest challenge, but this is not my job, so I will just say that the other challenges are way harder. And so I will just limit myself to crypto and maybe there, because... so about post-quantum crypto, this we need. So there's no way around this. We will need this. I mean, even if there's like a 90% chance that the quantum computer is developed, this threat is way too big to not do anything. So we clearly need post-quantum encryption. And I think the nice thing with this process and with the field that is getting like recognition is that it draws more people, it draws also funding. So I think there, I mean, more people is always nice and needed, but we're in a nice dynamic. At least there is research to it. So yeah, we need more research, but this is a good dynamic there. You also see that in the last years, there is a shift towards making these schemes practical. I think there we really need to up the work. So in 2 papers recently, we've discovered vulnerabilities in proposals where they had a security proof, they had measurements, and we still discovered vulnerabilities that were exploitable, that you could attack in protection mechanisms. So, I mean, and these people that made these schemes are good researchers. So this is not an attack on these people, it's an attack on... this is hard, like, how do we know that something is secure?
But these were not cases where the proof was wrong, these are cases where...
The proof was wrong.
The proof was wrong. I had another question, which I think you mentioned in your thesis on work that you didn't report on in the thesis, but you did on the side, this attacking the arithmetic to Boolean conversion from the Braze. You also write something like this: with this work we showed that it's important to also do an experimental verification of theoretical masking algorithms, as errors are quickly made and hard to spot in a theoretical setting. So was that also a proof that was wrong?
Yeah, so this was well, in this case, this was a paper by, like a more mathematical paper, but they said the proof is straightforward. Just look at this proof from this other paper and then just straightforwardly adapt it. And well, it was not that straightforward because there was a problem in the proof.
Okay.
But also I think, and this is cool to see in recent years, is that there is also collaboration between more mathematically inclined people and people that actually do measurements on this. And I think this is really a step forward because we both have security proofs, because if you don't have security proofs, especially for things like masking, I don't trust it. But also we have people actually checking in practice whether there is this assumption, because you make this tiny assumption, this will be correct, and then this assumption turns out not to be true, and you can just break everything.
So I agree with you very much. I think that's very valuable. But I also would say, I don't think that way you find all the issues in a proof. Not always an issue in a proof can be found with experiments. So we face similar problems in programming language theory, where small errors in a proof can lead to problems. And what people do there is machine check their proofs.
Yeah, this is also
so I wanted to ask you, is that the direction that crypto should go into or is going into? Or?
There is actually work towards this. So people are now checking the security proofs of Saber, Kyber. There is work into this. So this is really cool. I haven't done any work on this myself, but you see people moving into proving, making the security proofs machine verifiable. So a machine is checking if all of the steps of your proof are correct. So this is really cool. Even then, these are all security proofs, so you make assumptions and you need to be very careful on what model you use, because you're always using a model, and you should not forget that you're using a model. For example, the security of proof of Saber does not take into account side channels, does not take into account all these other threats, so it just says, this is what we can prove. And this is really nice, and this we should really do. So but yeah, look, all of these things like formal proofs, having proofs, experimental verification, trying to attack things, I don't think we can miss any of them. We really need the combined effort of all of them to get something that we can trust.
Okay, thank you very much. No more questions.
I'm going to add, it was a great presentation, really good. Thank you very much. Can you go to page, slide 24? I had a question on slide 24, but I've forgotten what it was, so I have to go back to it.
So the pointer is not working anymore again. I don't know what it is. It's a Zoom thingy. Yeah, okay.
Something on 24.
24?
It was 24, yeah. Oh, yeah. Here we go. What's this error distribution? You said you haven't got any error distributions in Sabre. You said that, or is this the error distribution for the secret key choice?
So the secret key in Sabre is binomial.
Ah, okay, so
and
that's what you mean.
The error introduced because of this cutoff is uniform, or at least
so it's
nearly uniform.
So it's not error distribution, it's secret key distribution in this table should be, yeah?
Ah, yes. Very well spotted. I just put that in there to see if...
see if someone spotted, okay.
Well
so
spotted.
I was going like, really? Okay.
Very well spotted, yeah.
Okay, so a basic. Okay, actually, go back a slide. Is it back for one of your pictures? Just any one of the yeah, that'll do. That'll do, right? So at the end, that's been hidden by the things, but let's not worry about that. You've basically got m plus some error times some other error in some sense at the end. Yeah.
So I got m plus
m plus something small times something small, which you can kind of think of as error things or secret times error or something like that. Yeah. Okay. And then what you say is that some schemes apply error correction to that.
Yes.
Yeah. Because the error times error is in some sense an error, and therefore you can error correct it.
Yes.
But in the ring setting, isn't error times error not independent? In other words, if one coefficient breaks if you have error times error, yes, polynomial times polynomial, if one coefficient of the product is big, isn't there a higher probability that another one is big, that they're not independent samples? So you can't, so you shouldn't really be able to do normal error correction, yeah?
Yeah, so this is these dependencies. What you describe here is essentially, if you're not careful, then you have these dependencies. So it's not a one-to-one mapping. It's not that all these coefficients are the same, of course.
No.
But and actually there is this, if you have a vector, you have like the length of S times the norm, the length of the norm of S times the norm of C times the cosine between the two. And so these norms will be the same. So 2 out of 3 of the properties will be the same, and then the cosine will be different. And so these norms will cause dependencies. And so that's why I said that if you want to use error correction, then make these norms constant, because otherwise you're going to have these dependencies.
Okay.
So if you make these norms constant, then you avoid these dependencies. You avoid that if one error is there, that another error is also there. And by avoiding that, you get rid of at least most of the dependencies, and these dependencies will not work against you that much.
So in your follow-up work then, could you relax that a little bit and use error correcting codes that don't assume that the errors are dependent? So if like you can have burst codes and things like that, where you kind of assume that the errors come in bursts, or or whatever fancy error correcting that you want to do. That might be a way of tweaking parameters to change things.
Yeah, so the problem is that it's not in bursts, it's in everything. So like burst directing codes would be nice, maybe in a setting where you're like a Frodo-ish, like more towards you have multiple polynomials and such, but that doesn't work here because, the burst is everywhere. So if the burst is everywhere, what are you gonna do? Maybe there is, but I don't know, because it's really all the bits. It's like it's kind of like the whole error probability goes up. So what are you gonna do about all the coefficients having a bit bigger error probability? I don't see a solution to that, because you don't know where you have to look. In burst, I'm looking locally, but you don't know where you have to look. So I don't know if you can really do something there. But this is if you just use error correcting, but you can go more esoteric. And I mean, for example, this is just an equation, and you have some of the things of the equation. So this could help you solving, like, you already know something. You know, for example, the public key, which is an LWE sample, but now you essentially get a hint to the LWE sample. So maybe, and we try to do this, but this is essentially a hint towards Alice's LWE sample.
Yeah.
So maybe you can use this hint to break Alice's LWE problem, and then it's another way to decode.
Yeah.
I mean, this is just random ideas and probably will not work. But I mean, this is these long shot ideas that you could use, and that's what I mean with different error correcting techniques. Maybe we don't need error correcting codes. Maybe we just need to look at the formulas and try to do our own thing, because we have very specific properties here and we can use them. Another thing is this confirmation hash, where you can actually send over a hash of your message, because it's not a channel that is noisy, it's this thing. So you send over a message, and because you have this, most of your coefficients will be centered around 0. And so if there is a coefficient around q divided by 4, then it's probably this coefficient that is failing. So you can make a list of ciphertexts that are most probable of failure. You don't have to check all of, like, you can say probably it's one of these 5. So if you send over a hash for confirmation, you don't have to check all of the errors. You can just generate a list of all the coefficients that are close to this boundary that you don't trust, because most of the coefficients you will be able to trust. I mean, the probability that your error gives you a half circle is nearly 0. That will never happen. So these kind of things is more what I'm pointing towards. Like, let's think out of the box. Now we just use error correcting codes, which is a great way to start, but we can do better, no? I mean, yeah.
Okay, cool. So Damien asked you what you would change if you started again.
Yes.
Okay. I'm going to ask a much more higher level question.
Uh-oh.
What would you change if NIST started again?
Okay, so if I am NIST?
If you were NIST, what would you have changed? What do you think they should have asked for? What do you think conditions should they have set, or metrics that they should have chosen that they didn't choose, etc., etc.?
Okay, so let me first start with saying that I think NIST is doing a great job. So I mean, this may be important to say because you can always critique somebody,
And
but
you don't know who's listening.
What?
And you don't know who's listening.
Yeah. Hi NIST, if you're offering a job, no. I think they're really doing a great job. So one of the things, at least as a team, we went into this and it was really hard to know what they actually meant with. I mean, there's this document, we're looking for post-quantum encryption, and I think they themselves, just as everybody in the community, just didn't know what we wanted. Like, what do we define as secure? What are the borders, what are how much overshoot in security do you want to have because there is script analysis? This was not clear. We had long discussions on what these security things actually meant. Like, what do you mean with security in this thing? I think it's also because we just got started and we didn't know it as a community. So, I mean, it's hard to critique them for that, but if I would start now, I would define better measures to say this is what we want as a security. Also because we have all these schemes and then they're tested on performance and they need to have the security level, and so teams are like undercutting each other in security because then you get better performance, and then they make like these reasonings that, yeah, but it is secure because of this and that, and then you get a race to the bottom. So this is not what you want, because you want like very secure schemes. And of course, for some schemes, it's turned out to be a bad bet because they went under the security level. But I think this is something like clarity, like this is what we want. This is what the standards guess. Also, I think, but this is coming now. It is a focus on, for example, implementations on side channel protection, these kind of things. But yeah, maybe that's also not needed in the first part, because you first want to do cryptanalysis and then move on to the next part. So I think that is fine that it's only coming in the third round, even though, I mean, they'll have to decide in a year, and I don't know if everything is going to be ready to decide. But yeah, I mean.
And now I want you to be completely unpolitical to this, and I want you to say, was there any candidate in round 1 and round 2 that they kicked out that you think they should have kept in?
Kept in?
Yeah.
Okay, I really like Tree Bears. Maybe it's not practical, but it's. Have you read the submission document? It's amazing. So this Mike Hamburg, he only wrote it. I still think it's a whole team behind it. I mean, this guy did all the work. This is amazing. But also he made like these amazing choices where he said, I did this because nobody else did it, and I just wanted to put it out there and see if somebody can break it. I think it's secure, but I just want somebody to try to break it, so I put it out there. So I just love this submission document. He made all these weird choices, but not weird because they were actually secure and there's nothing to say about the scheme. So yeah, maybe we should not standardize it, but make it like a Dogecoin version of post-quantum crypto. I don't know, but I really like this scheme. Then like was kicked out, and I think this is for the best now, but in the future I think this idea will make a comeback. But it's not ready now, so yeah, I think it's right that they kicked it out, but yeah, especially the first version of like I really liked. Then they started adapting it and was less a fan because they started to do this like tweaks to still get security, and that's never good. If you start to like do small things instead of looking at the whole thing, this is never a good idea. So yeah, the first version of LAC with tweaks, I think in the future will come back, but it's not ready yet for this process. Yeah.
Okay, thank you very much. That's all my questions.
So Jan-Pieter, also congratulations from me, of course.
Thank you.
I don't have many questions. We had lots of discussions already.
True.
But maybe one, which is inspired by your slide on LWE. So if you can go back, I think a couple of slides.
This one?
No, you have the slide where you have the 3 versions. So where you have the integer, polynomial.
Oh yeah.
Oh yeah, it's further down. Yeah, that
this one.
So yeah, this one. So. Especially the left one, are you saying they're all equally secure as they are written here? Or?
So what I did to calculate the left one, I mean it works, so you can. But so this is the left one was actually just to get my grandmother also understanding this, and she doesn't know matrices, so I made up a scheme there, and it's actually possible to make a scheme. What I did to calculate this number is, I think I took tree bears, which actually uses numbers but then specific properties, and I just took like kind of like the size that tree bears uses. So this, if you translate it, is going to be kind of like the same security, but I just took tree bears. It works with like vectors also, but I just assumed that this was one big number, and then cheated my way a bit over there. But this is not a real scheme, but it kind of is like in the right ballpark.
So would you say you can exchange, because if you look at the second and the third column, right, you have matrices and then you have matrices of polynomials, but the overall size is still the same.
Mm-hmm.
So is that what gives you the security, that the overall size is the same also in the first one, or?
Yeah, I mean, should be, yes. I mean, this is essentially tree bears where I removed like so if tree bears is this, then I move to this step. This is essentially what I did with tree bears going to this number. So if this step is valid, then that other step is also valid, but don't take this as advice. I mean, take this as, I think it is. Yeah, probably this. I just did the same step from here to there, and then I took tree bears and I did the same step to get there. Mm-hmm. But this is more like a recommendation so that my grandmother has an intuition about the sizes that we're working with.
Okay, thanks. That way.
Thank you. Thank you for your nice presentation. With all your indeed skills and training, you give very nice presentations. I like the Saber. I'm going to ask, as you know, I'm a hardware implementation person, so my question is going to be that direction, and I think Sujoy asked some questions already in that direction. Mm-hmm. So I like it that Saber takes quite some hardware implementation aspects into account. Yes. So the fact that you use simple rounding instead of that you use modulo 2 arithmetic and things like that. You also mentioned a few times IoT in your thesis. So I have a few questions in that direction. In sense, in IoT, we actually were much more worried also about low power, not just size. And one of the tricks that people use for low power and low energy is to use what's called approximate computing. And approximate computing also introduces noise. So it's a little bit more advanced than just truncating. What you do now is truncating and a couple of correction vectors. But what would happen if I mean, reducing the power with a few percentages you can gain a lot. Your battery will last much longer, things like that, right? Could you use things like that? So you do calculations and occasionally one which has a long critical path will not finish?
Okay, so I will start with the fact that we kind of use this. If you look at side channel protection algorithms, we kind of use IDs there because sometimes we do not need everything in the whole calculation, so we use essentially methods that do like a whole transformation, but then there's some bits we don't need, so we throw these bits away, or we don't calculate them, and so we prune the whole algorithm for things that we don't need. So in essence, it's the same. It's a bit the same idea that we use there. Now, if you really want to go for like probabilistic approximate calculations, again, you're gonna run into the same problem with this re-encryption. So the ciphertext that you compute really needs to be the same as the other one ciphertext. And if you cannot guarantee that, you will have like this collisions where you think you input a valid ciphertext and then the adversary, or you're not gonna be accepted, and this will give away information. I mean, this approximate calculation will probably be dependent on the secret. So I see a problem there. So I don't see a problem if you do it, for example, in key generation, even though you have to be careful, because if the noise becomes too big, you really have big problems because of the decryption failure attacks. But no way you can use it in encryption and in decryption if it's not deterministic and if it's not exactly the same for both parties. So this would be a big constraint.
Yeah, exactly the same for both parties will be difficult because my encryption could or my decryption could happen on the node and the encryption decryption on the server, right, or on the cloud. Which
so if it's probabilistic, you cannot use it.
It's not really probabilistic. You can probably predict where the errors were going to happen. Related to that, also from a power perspective, we really don't like these huge hash functions. They consume area, they consume power, they are tough to mask. Can you come up with something better?
uSaber. So in uSaber, we need less hash functions. The idea there is that your secrets needs less random bits. So you can reduce the hash function calls for the secret keys.
But
like
one of the reasons that hashes are chosen is that you don't have to transmit. You just only have to, agree on the. You only have a seed, and then you create your big functions.
Okay, so you need hash functions for two things.
Yeah.
The first one is that actually this matrix A, you don't transmit the whole matrix, but you transmit the seed, and then you do the calculation.
Yes.
So this matrix A probably I guess, but again, we need to look into this as a community. But I guess, for example, for this matrix A, it will be all right if you do only half of the hash rounds. Because you don't need security there. You just need to have a statistical uniform distribution for A. So I don't, because this is public. The input is public, the output is public. So I think there you can do something, but we really need more research into this before we really do this. But this is an interesting research action. And the second thing is this S and E, this is critical. So really here you need these bits, they need to be very pseudo-random, all of this. So the only thing you can do is reduce the number of bits you need, which you can do in two ways. One, use Saber, because if you use Saber, you don't have to generate ECs, which is nice. So half of the randomness, more or less, you need. And the second thing is that in uSaber, so in Saber we have this binomial with 8. So you need 8 coins, so 8 bits for one coefficient. In uSaber, we have like a uniform distribution with width 2. We only need 2 coefficients, so that's a drop factor 4. So if we go from like any LWE scheme to Saber, we have a factor 2, and if we go to Saber, from Saber to uSaber, we have a factor 4. So in total, you can gain a factor 8 in hash functions there, and then maybe you can gain a factor 2 in the hash function to generate A.
Could you vote, you need it uniform, could you simply use a high quality, just true random number generator, very compact?
No, because again, so for this random, well, you can use it for Bob. Bob can use it
Yeah.
because he just needs random numbers. Nobody's checking it. Alice cannot use it because Bob is gonna need the same number. So he needs to, from K, recover this S prime, E prime, and E prime prime. So here, Bob's secrets, we can do it. I don't care how you generate it. It just needs to be random. Alice needs to be deterministic based on a seed because otherwise we cannot do FO, the Fujisaka-Okamoto transformation. And then for A, we also want the deterministic hash function because we want to send over the seed. Otherwise, you have to send over the whole A, and this is going to be a mess with bandwidth. So the only part where you could use true randomness generations is Bob.
And for your seeds.
And for your seeds, of course. You need the true random numbers for your seeds for both Bob and Alice. And they need to be good randomness because otherwise, again,
otherwise you have the problem of bias.
Yeah, definitely.
Okay, thank you.
Zo, Jan-Pieter, dat waren de vragen van de leden van de examencommissie. Dit is een publieke verdediging, dus u weet dat iedereen die hier aanwezig is het recht heeft u een vraag voor te leggen. Bij voorkeur in verband, in dit geval, met Lattice-based post-quantum encryption. Zo. Zijn er vragen vanuit het publiek?
Stel gerust. Er zijn ook geen vragen online. Dus,
Nee.
Voilà.
Heeft u de micro nodig?
Nee, doe maar, Ton. Stel maar. Oké, heel interessante vraag. Dus de vraag is, want de mensen online horen het niet, de vraag is of dat de 4 finalisten voor die encryptieschema's hetzelfde zijn of verschillend. Het antwoord is dat 3 daarvan komen uit dezelfde familie, uit die lattice-based encryption. Dus zijn verschillend, maar binnen dezelfde familie. Dus waarschijnlijk delen zij wel dezelfde security achtergrond. En deze schema's zijn eigenlijk heel goed all-round. En daarom zijn ze hebben geen breekpunten. Dus er zijn geen punten waarop die schema's echt heel slecht zijn. Dus daarom zijn zij wel heel geliefd in... I should talk in English, sorry. So because of that, people like them a bit or work a lot on them, and there's 3 of them selected. Now, because we don't want to stake all of our security on just one scheme or one family of schemes, there is actually also a different type of scheme in this competition. And also there are 4 follow-up schemes. So they're not really considered for standardization, but they're like backup. So what if these 2 families that we have left, what if they completely break? Well, then we have this backup. So this is also an important thing, is that, of course, we want to maybe dedicate all our efforts on one type of scheme, but this is not a good solution because maybe it's efficient, but what if it's broken? So we need to divide our attention over multiple families of schemes that have vastly different security properties or guarantees. So, yeah.
Is dat voldoende als antwoord? Nog vragen? Indien niet, dan zullen de leden van de examencommissie zich nu terugtrekken voor een finale evaluatie.
Gaat je mij in een breakout room zetten of ga ik eruit? Oké. Super, dank u wel. Zo, dan deze is blij. Merci om te komen trouwens allemaal, dat is heel leuk. Dank je wel. Ja.
Dus je stond in het moet het niet. Dat is, dat is het probleem. Is dat belangrijk?
Ja, je bent in het publiek, hè. Wacht, ik ga waarschijnlijk straks in de... Oké. Ja, zeker, zeker. Ja, die van u was echt wel de moeilijkste. Nee. De vragen waren ook wel aangenaam, omdat het is wel leuk om uit te zoomen en terug te kijken. Tijdens mijn privéverdediging, of dat is waarschijnlijk altijd het geval, krijg je zo meer specifieke vragen. Wat zou er gebeuren als je nu probeert dat schema te doen, maar je probeert die security garanties of zoiets. En dan wordt het ingewikkelder, dus, maar nu is het ook wel fijn dat het een ander type vraag is, maar nog altijd wel challenging in a way. Van, je moet er echt wel over nadenken van, oké, wat is de hele context? Maar ik vind dat wel leuke vragen om te beantwoorden, omdat dat u dwingt om een stap naar achter te zetten. Want je zit zo dicht op dat werk, dat je soms het nodig is om zo'n stap terug te nemen en te kijken van, oké, maar wat is de brede picture? Ben ik nog altijd nuttig bezig? Dus in die zin zijn dat wel leuke vragen, ja. Ai. Ja. Ja, en het leuke is, dat zijn geen ondervragen, dat zijn geen juist fout. Geen van die vragen is juist fout. Het leuke is dat de jury ook gewoon geïnteresseerd is. Of de vragen die ik nu gekregen heb, daaruit blijkt dat de jury eigenlijk echt wel wilt weten wat dat uw mening daarover is. En dat is gewoon fijn, want dat betekent toch ergens dat er appreciatie is voor toch een beetje kennis dat jij hebt binnen dat gigantische domein. En het leuke is ook dat alle juryleden, misschien, ik weet niet of je dat door hebt, maar alle juryleden hebben een heel andere specialisatie. Damien bijvoorbeeld is meer wiskundig, is meer naar proeven kijken. Sujoy en Ingrid zijn gaan meer kijken naar hoe gaan we dat dan maken en wat zijn de problemen als we het gaan maken. Dus dat hoort dan ook in die vragen. Hè, van, sommige vragen zijn heel wiskundig, van wat als we nu dit doen of wat als we nu die errorcorrectie gaan aanpassen, terwijl anderen dan meer gaan naar oké, je wilt dat nu op een Intel-processor zetten, wat zijn de problemen dat je gaat hebben. Dus dat is ook wel leuk, het feit dat je geen jury hebt die enkel uw werk kennen, maar ook jury die van andere... Maar bijvoorbeeld Frank Pieces, die hier zat, die zijn expertise is meer hoger level. Dus die zit meer op zo... het grotere geheel protocollen en zo. Die doen dan bijvoorbeeld aanvallen op wifi en zo. Dus dat is een heel ander gebied, maar die stelt dan ook vragen die daar meer bij zitten. Dus ja, dat zijn toffe vragen. Wat als we binnen een jaar geselecteerd worden, dan gaat er champagne open. Dus de vorige standaard, dus die AES, die in Leuven is ontwikkeld, dat was eigenlijk een van die vorige competities. En dat is de Amerikaanse standaardisatie, maar de facto heeft heel de wereld dat overgenomen. Dus heel de wereld, als jij nu iets doet op je computer, dan gebruik je dat. Dat is gewoon de standaard. Dus als wij worden geaccepteerd, dan zou dat waarschijnlijk betekenen dat binnen 10 jaar op elke computer ons algoritme runt. Dus dat is super cool, want letterlijk elk stuk elektronica gaan opzetten, daar zit uw algoritme op. Nu, 1 op 4 kans. En gelukkig zijn de andere kandidaten ook goed. Dus het is nu echt kijken naar welke dat zo de fotofinish haalt. Goeie vraag. Ja, ik denk, als er meerdere gaan selecteren, dan op deze moment denk ik dat het meer gaat zijn om security. Dus de vraag is of er één of meerdere gaan selecteren. Ik denk dat als op deze moment dat meer het concern is van we moeten iets secure hebben. Efficiëntie maakt nu niet uit. We moeten echt gewoon klaar zijn als die quantum computers komen. Dus als er meerdere selecteren, denk ik eerder dat is omdat ze een backup willen hebben dan omdat ze echt te gaan. Wat ik voorzie binnen 5 of 10 jaar is dat ze een soort lightweight gaan doen. Dus waarbij dat je bijvoorbeeld gaat zeggen, wat voor ons belangrijk is dat het snel is. Of wat voor ons belangrijk is dat de bandwidth, dus wat je overstuurt, klein is. En dat maakt niet uit dat je dan dubbel zo lang moet berekenen. Bijvoorbeeld als je draagbaar en je moet meer signalen oversturen, kost dat veel energie. Dat kost veel meer energie dan je rekenwerk. Dus ik verwacht binnen 5 of 10 jaar dat ze wel naar die gespecialiseerde dingen gaan en daarvoor gaan bijvoorbeeld die error correcting codes en zo nuttig zijn. Nu zijn ze echt aan het kijken naar wat is allround oké. We moeten niks snel hebben, we moeten oké zijn. Ja. Moet ik weggaan? Ja, we horen ze toch niet, hè, dus. Ja. Wij hebben zelf geen patent genomen, omdat als je een patent neemt, dan is het probleem dat als er een gratis alternatief is, dat mensen daarvoor gaan gaan. Dus NIST heeft ook aangemoedigd van iedereen om geen patent te nemen, omdat je dan ziet dat mensen het gewoon gaan vermijden. Maar een van de issues is natuurlijk wel dat er patenten zijn. Een van de issues is dat er patenten zijn en... Kom binnen. Waar zet ik mij?
Dames en heren, geachte collega's, ik geef u kennis van de uitslag van de beraadslaging van de examencommissie, aangesteld voor de proef van dokter in de ingenieurswetenschappen. De heer Jan-Pieter d'Anvers heeft aan de faculteit een proefschrift voorgelegd handelend over Design and Security Analysis of Lattice-based post-quantum encryption. Ontwerp en veiligheidsanalyse van roostergebaseerde post-quantum encryptie. En dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. En hij heeft dit proefschrift in een openbare zitting voor de examencommissie verdedigd. De examencommissie heeft vastgesteld dat zowel aan de wettelijke en decretale bepalingen als aan de voorschriften van het universiteitsreglement ter zake werd voldaan. Na beraadslaging verklaart de examencommissie dat de heer Jan-Pieter d'Anvers voldaan heeft aan alle eisen voor de proef en de graad van dokter in de ingenieurswetenschappen behaald. Bijgevolg en in naam van de rector van de KU Leuven wordt de heer Jan-Pieter d'Anvers gepromoveerd tot dokter in de ingenieurswetenschappen, elektrotechniek. De zitting is gesloten. En naar goede traditie zal denk ik de promotor nog een woordje vertellen over leven en werken van de kandidaat. Nu dan.
Congratulations, Jan-Pieter.
Ja, want anders kunnen mensen het niet horen. Dit zou moeten werken. Ah, is het op mute? Nee, dit zou moeten werken. Ja.
Ja, proficiat Jan-Pieter. Congratulations Jan-Pieter. Really nice work. And usually at the end of a PhD defense, when all the official part is over, we give you a few small words, final words. So as you can read in his thesis, Jan-Pieter started his PhD in my research group in January 2017. And at that time, we actually both agreed that accepting him as a PhD student actually came with a lot of risk. There's a little bit of high risk because they decided that it was, because I know it's difficult to switch research to start a new topic, but I think the best moment to do this is actually early in your PhD, right, in your research. And I think this risk was actually even much higher for you than for me. The only thing I would lose is maybe some funding. You came with the recommendation of Peter Mane, and that's already reduced the risk a bit for me. And you turned out quite opposite in the sense Peter was very applied, very practical. You came out quite mathematical, I would say. So I still think this was a very brave, dapper, we would say in Dutch, to take this action. Now it turns out you flourished during these 4.5 years, and I think you took all occasions that we offered you. So one of these things is that I usually encourage my students to broaden their network and to go international. Peter went all the way to the US to do an internship with, in San Francisco. You also took this to this heart and really used your PhD time to broaden your network. We've seen that in the PhD jury. We've seen how many people are co-authors. I mean, you nicely have broadened your network. I think it also helps because you're quite open to other cultures. You're open to people with different backgrounds, coming from different countries. And I remember, you planned this really long trip to China. I don't know how many months you were gone. But he had a plan of combining workshops, summer schools, university visits, and in between a couple of weeks of vacation to explore the country. I think that was nice, and I think shows how open you are to other cultures. And I think you were going to do the same thing with the US last year. An invitation to go to Berkeley, was going to go to Microsoft, I don't know what other things. But then COVID came and you nicely stayed here. All plans, things. I like your work, I like your results. Maybe realizing afterwards I would have loved to have you a bit more in the lab, but you wrote in your original email that you wanted to do more mathematics. But maybe now that you're going to work on masking and side channel, you can gain some practical skills also. That would be nice. What I also like is all your, or appreciate is all your work for science figured out, science battles. The university needs someone to explain their science to the general public. I think you do that very well, it's also shown today. So I appreciate those things. Now, the last thing is I also have to congratulate you with your FWO postdoctoral fellowship. Yes. This was announced this morning. And I think Kosik did very well.
Yes,
so we had 3 people with a postdoctoral fellowship. So congratulations with that. And overall, thank you for being part of our group.
Thank you. I would also like to say a few things, if I find it. So, is there a doctor in the room? Yes, there is now. I've worked 4 years to make this stupid joke, and it is completely worth it. No, but seriously, it's really an amazing honor to receive this PhD, to receive this paper with my name on. But it also feels a bit weird because it's like my name on this paper, while I don't think this paper is only my merit, because this day is only possible because of so many people that helped me, that guided me, that were just there for me. And so I want to thank you all. Unfortunately, that's not possible because I don't want to bore you with like a 5-hour thank you. So I will just, I thanked already a few people here. I will thank a lot of you when we see each other again in a bar. But I want to thank a few people in special, which I will begin with you, Ingrid. So thank you for taking the risk to taking me on, because I know like my position was a bit weird. I just stopped another PhD because yeah, there was nothing for me. Then I jumped. I didn't understand anything. So you gave me papers. I didn't understand it at all, but yeah, it felt good. So I made the jump, and yeah, it was an amazing journey. Also, you've given me a lot of possibilities. Like if I wanted to do a course on, I don't know, patents, then I was allowed to do that. I was given the money and the time to do that. Yeah, you've given me so many opportunities, and I'm super grateful for that. I've really grown as a person thanks to all of this, thanks to you. I also would like to thank Frey. Frey, you've thought, well, Frey, maybe some people know, but I'm a bit intuitive and also a bit slordig. I don't know how you say that in English. Yeah, my thoughts are a bit sometimes going quite fast and coming. And so Frey, really, you taught me how to formalize these thoughts, how to write them down in a paper. I remember the first papers that came back, these mathematics, they were completely red because I didn't have my mathematics in order. I didn't know how to write all these things. So you really taught me how to formalize my thoughts and how to yeah, bring my ideas across to other people, and I'm really thankful for that. I also want to thank you for all the very nice whiteboard discussions that we had. I also want to apologize for the rest of COSIC if we were too loud when we were discussing sometimes. But yeah, I really appreciated these moments. And I also want to thank the rest of the jury, because I actually explained it when you were gone, but it's really nice that I have a diverse jury that read my thesis and that asked interesting questions. I mean, I worked 4 years for this, and then it's really nice to have a jury that at least seems, but if it's not, then you did a great job, but a jury that is interested in your work, that asks hard questions, but questions that show interest, and that really makes a difference. And for me, that makes this day actually more worth it. So I really want to thank you and also the jury online for the nice questions and for reading my paper, and also the jury members that I worked with during my PhD. I would like to thank them for the nice collaborations, the nice discussions for that. I also would like to thank my previous promoter, because I said before that I quit another PhD. I think it's important to say that my previous promoter was really a good promoter. I quit because artificial intelligence at that moment was not for me. The research was not for me, and I'm still happy that I made the switch, but I want to say that so Tinne Tuitelaars, my previous promoter, is actually a very good promoter, and that is, it's not her, but it's me. This sounds weird, but yeah, no, I really want to have said this. I'm halfway, so I'm not going to take you too long, but I also want to thank all of my teachers. This is maybe a bit weird to say, but I mean, I'm only here because of the amazing teachers I had, the amazing professors that I had, the teachers at St. Levis, but also the professors here, people that, for example, from Science Figured Out, all these people taught me so many things that I could showcase here, and without them, it would not have been possible. These people did their work, but they did more than that. They did their work with passion, and that is just so nice, and that is why people like me are happy to be here and can be here. So yeah, thank you. I would also like to thank my co-authors. I worked together with a lot of people, and all of these collaborations were amazing. Like, just to work together, like 1 + 1 is not 2. You can do so much more. You can learn so much more from them. But above that, they were just super nice people. It was super nice to work with them. Some of them are still friends. Some of them are watching now. Even if they're living in France or in the UK, it's just nice to have friends, gain friends in what started as just writing a paper. I want to expand that to the whole cryptographic community. Actually, we have a really nice community. So if you're looking for, we have a really nice community. People are really open. People share ideas. You can ask for code. People will send it to you. And I think this really accelerates the whole community. But also, I mean, if you're then at a conference, you go for a beer afterwards, like the atmosphere is nice. You really make friends for life. And I hope this stays this way, because this is really cool. So to end, I want to thank all of my friends. So if COVID learned me one thing is that I miss you. That really, I mean, yeah, sitting at home is not for me, and I cannot wait until I see you. I'm gonna cry, shit. I cannot wait until I see you in a bar. I mean, I've been missing you, and just online is not good enough for me. So let's hope we get vaccinated soon, and let's hope we can meet in a bar, just discuss everything. And thank you for being here also. This morning I got so many messages saying saying success, and it's just a small message, but it does so much. So really thank you for being here online, for being here in the auditorium. Yeah, that is really nice. And then, as Stone points out, but I did not forget them, my family. So in this auditorium, there is my family, and I've wrote something about them here, which is, you cannot choose your family, but I've been blessed with such an amazing one. And this was actually not the original sentence, but I didn't want to be too braggy in my thesis, but I will just say it. The original one was, you cannot choose your family, but I've been blessed with the most amazing one. And I thoroughly believe this is true. You're just the best family ever. And I'm going to stop here because boys don't cry. But yeah, thank you for everything. And thank you for being here. And let's just have a drink in a bar once we see each other. Yeah, thank you.